In this video, I will explain you what is mutual induction. In the previous video, I have explained you what is self-induction. See, in the self-induction, there is no two coil, only one coil. Current is passing through it. It is creating magnetic field around it. Now, the magnetic field line is linking with the same coil, so there is a flux linkage with the same coil. Now, whenever current is changing, magnetic field changes, magnetic flux changes, so there is change in magnetic flux linked with the same coil. And as per Faraday's law of EMI, there will be an EMF induced here. Reason is there is change in magnetic flux linked with the same coil. Here the reason is due to the current changing with the same coil. Now that will be the induced EMF. Now in the case of mutual inductance, it is more easy here because this is creating a magnetic field whenever current is passing through one coil. Now another coil has no current in it, but whenever this current changes, this magnetic field will change. So see, this field is being linked with different coil which is placed in proximity. Now see, whenever current changes, magnetic field around it will change. Now whenever the magnetic field changes, magnetic flux linked with this coil changes. Now as per Faraday's law of EMI, there will be an EMF induced in it. So that is the meaning of mutual induction. Mutual induction is a phenomenon in which flux linked to one coil varies, that is with this coil varies according to current change in different coil. This is the different coil here when it is placed in the proximity. Okay, now as per the equation, flux linked with magnetic flux linked with, this is one first coil, second coil, linked with second coil is equal to, is directly proportional to current passing through the first coil, because this current makes a flux here. So in the similar way we have learned for mutual induction, there also I have told you flux is directly proportional to current, but here it is mutual induction. So I can say that flux linked with 2 due to 1. Previously I have mentioned only one flux because on the same coil, so I don't have to mention numbers here, but I have to mention number here. On 2 due to 1, so current is going through 1, so I have to mention this is the reason here, 1 is the reason. Effect is happening on 2, so current going through 1 is linking a flux on second coil. So this constant of proportionality is the coefficient of mutual induction. So phi 21 is equal to M21 into I1. Very important relation, this one. Now how to get the value of induced EMF? See, this is changing, right? Whenever I1 changes, this value changes, and that is creating an induced EMF in 2. So induced EMF in E on 2 is equal to minus d by dt of phi 21. So here phi 21 is this, so d by dt of M21 into I1. So M21 is constant, that will come out M21 into di1 by dt. So current in the first coil, whenever it changes, that will induce a EMF on second coil. See, as per this equation. Now we need to get the value of M21. For that we will get one more equation for flux, then we will equate both the flux. Now flux on 2 due to 1 is equal to, we know the equation for flux, that is BA cos theta. Now here what will be cos theta? See, this is area vector will be in this direction, and flux magnetic field also will be in this direction. So cos 0 1, so that will be B on 2 due to 1 into, now which area you will be considering, the smaller area or higher area? Basically I have to consider this area because flux is linked on 2, right? Reason is 1. So here I have to consider field at here and area of this. But the problem here is whenever this is small, then the magnetic field lines will be only passing through a small area. See, let's say this is coil 2. Okay, coil 2 it is. Now this is the coil 1. Now magnetic field lines from this coil will be passing through this area, but it will only be a smaller area. See, we have only magnetic field lines with this area. See, this is the coil 1. that is being linked with coil 2. So only on this area we have magnetic field lines passing. So we have to only multiply this area with this field intensity. See, all other places magnetic field is 0, so flux will be 0. So always take the smaller area. So I am going to represent, see, I can use A1 or A2 here. We don't know which one is smaller, so I am going to define that A1, considering that A1 is the smaller area. That doesn't mean that area of this one, whichever is having the smaller area. If the experiment is in this way, if this is big and if this is small, then still in that case you have to take area as this one, because that will be the effective area. So out of A1 and A2, out of area of one coil and another coil, take the smaller area, and that is now going to represent as A1. Now A1 means out of 1 and 2, 1 is smaller, so A1 represents the effective area, and that is the smallest of these two areas. So B21 into A1 cos theta is cos 01. Now magnetic field flux due to, one more thing, now length of both the coils are same, okay, and we know that number density of this one N1 is equal to total numbers of this coil divided by length of this coil. Here it will be number density of 2 is equal to total number of turns in this coil N2 divided by L, and length are the same, okay. Now B21, what is magnetic field due to current carrying solenoid at this point? That is mu 0, and who is sending the current? N1 coil is sending the current, and the current is I1. Now this is magnetic field due to I1 at this position into A1. So out of these two, whichever the smaller area, that is A1. Now this value only represents the total flux linkage with one coil. Now if there are total n number of coils, here n2 number of coils are there. Now what will be the total flux linkage? Total flux linkage with all turns is equal to this into, so 521 total. This is with one coil, okay. In the derivation you have to mention one coil and total, that is this multiplied by N2, because that is going to get linked with N2, right? Mu 0, N1, I1, A1. Now N2 can be written as small n2 into L. Small n2 into L, mu 0, N1, I1, A1. Now we know that this flux and this flux is the same. So I can equate that as per 1 and 2, 1 is equal to 2, which means M21 into I1 is equal to N2. Yeah, rearrange it. Mu 0, N1, N2, A1, L into I1. I1 can be cancelled, and the equation will be M21 is equal to mu 0, N1, N2, A1, L. Very, very important relation. This is very important. Okay. Now, what will be the value of mutual induction, coefficient of mutual induction of on 1 due to 2? You can change the equation. M12 is equal to same thing, mu 0, N1, N2, A is anyway smallest of out of these two, so that will be A1 itself, and length is the same, and equation will not change. Instead of N1, N2, this will become N2, N1, but N1, N2 is equal to N2, N1. So mutual inductance of one due to another coil is equal to the opposite of this. Okay, this is very, very, very important. Learn the derivation. This is asked multiple times. And now how to get the value of mutual induction? As per this equation, EMF, induced EMF is equal to M21 into di by dt. This is the magnitude. Now when di by dt, whenever the rate of change of current in this coil is made to 1, that is 1 ampere per 1 second. If this value is 1 ampere per 1 second, then induced EMF, whatever you are going to mention here, that will be mutual induction. See, as per this will be 1 ampere per second. When this is 1, EMF is equal to mutual inductance of 2 due to 1. Okay, so this is very important. You can define M21 in this way also. When dI by dt is equal to 1, the EMF, induced EMF measured is equal to mutual induction. Okay, coefficient of mutual induction. Okay, thank you.